Hey everyone. In this video, I'm going to walk you step by step through the math to derive the OLS estimator in the bivariate case. So in the simple case where we have one dependent variable and one independent variable. But before we get to that, I just want to review some important concepts of covariance and correlation that we already talked about in previous lecture videos and that you've already encountered in the book as well. Remember that when we introduced correlation and covariance, we said that the correlation and covariance describes a linear relationship between two variables, in this case now xn and yn, where the subscript n indicates individual observations. Now, the population covariance between two variants can be defined as, here we use sigma squared and Greek letters in general for population parameters. So the population covariance between x and y is sigma xy, and that's the expectation of x minus mu x, so x minus the mean of x, the population mean of x, times y minus mu y, so the population mean of y, and the expectation of that. That's the definition of the population covariance. We also, of course, we don't observe the entire population. What we usually observe is a sample, and the sample covariance is then an estimator, or an estimate of the population covariance, and that is 1 over n minus 1 times the sum from n equals 1 through capital N of xn minus x bar times yn minus y bar, right? So that's just the sample covariance as an estimate for the population covariance, where here these mu's are not observed, the sigma is not observed, we don't observe the entire population, but we observe x bar and y bar, those are the sample means. And so this is basically just the sample covariance between x and y in our sample, okay? Note that the population and sample covariance lie in an interval between minus infinity and plus infinity. So 0 describes no linear relationship, positive is a positive relationship, and vice versa. But the important limitation to note here is that covariance is not unit free. So in other words, if we measure xn in inches rather than feet, for example, and we're talking about the covariance between height and body weight, for example, then the covariance, just by measuring one of the variables in inches rather than feet, the covariance would be increased because the scale is increased, okay? And so that's why usually we're when we're examining bivariate relationships between two, or linear relationships between two variables, we're focusing on the correlation. So the population correlation between two variables can be defined as, and this is now rho xy, and this is basically the population covariance divided by the product of the individual variances of x and y. So in other words, it's scaling the population covariance by the variance of the individual variables, right? And similarly, and this is now the kind of the main formula that we saw in the book and that we talked about, the sample correlation is then basically the same thing, just for our specific sample, where we basically divide the sample covariance SXY divided by the standard deviation of x times the standard deviation of y. And in the book, this is kind of, you can directly show that this is kind of mathematically equivalent to the basically the product of the z-scores. So xn minus mean of x, so that's again xn minus x bar here, times yn minus mean of y, so that's yn minus y bar, and divided by the standard deviation of x and the standard deviation of y. as we see here as well. So in the book, this is described as the correlation being equal to the mean of the products of the z-scores of both variables, and that's a very useful kind of way to think about correlation, as we talked about kind of what does it mean to have a positive relationship or negative relationship, linear relationship, of course, as kind of the product of z-scores, or thinking about observations being tending to be above the z-score in one variable implies that the variable also tends to have a higher value or a high z-score on the other variable, and that implies a positive relationship, for example. We talked about this in some of the previous videos. And compared to the covariance, the important thing about the correlation is that the magnitude of the correlation does not depend on the scale of the variables like the covariance, right? And so the scale of the variables and the population and the sample correlation, or sorry, the population and sample correlations, in contrast to the population covariance and sample covariance, always lie in the interval between -1 and 1, right? So basically you can think of the correlation as rescaling the covariance to be bound in the interval between -1 and 1, okay? And being unit free, so independent of the scaling of one of the variables, okay? All right, so after we kind of talked through those basics of correlation and covariance, now we can go to our OLS estimator. And we begin with a basic bivariate linear model. So we have one dependent variable, yn, and that is a function of our independent variable xn. The relationship between xn and yn is basically determined by beta, the slope coefficient, and we have the intercept alpha, and we have some epsilon n, so some error term. So one of the examples that we could that we talked about in the past is, for example, in chapter 4, where we talked about researchers predicting vote margins of Democratic candidates versus Republican candidates based on the competence assessment based on facial expressions, right? So this was one of these experiments that we talked about, where people were given pictures of two candidates and they were asked who would you rate more competent. And then the researchers examined to what extent the competence rating or the relative competence rating was associated with the actual vote margin in an election. So there the vote margin would be the dependent variable, and the competence rating on some scale would be the independent variable, okay? And so now recall that when we estimate the parameters of this model, we ultimately what we try to do is we want to minimize the sum of squared residuals, right? So we talked about kind of summing up all the error terms or all the residuals between our predicted y hat and the actual observed y, and we're taking the square of those residuals and we're summing them all up over all observations in order to get the sum of squared residuals. And then we just find the parameters alpha and beta hat that minimize those sum of squared residuals. And that's kind of what in the last week in our Q&A session, where I showed you this little shiny app that allowed you to try out different parameters and the resulting and it returned kind of the resulting sum of squared residuals, and you could kind of move your way towards the actual OLS estimators, okay? So the parameters alpha hat and beta hat that we obtain by minimizing the sum of squared residuals are the OLS estimates. That's what we call the ordinary least squares estimator of alpha and beta, okay? All right. So how do we find parameters or alpha hat and beta hat? How do we find our estimates that minimizes the sum of squared residuals. Well, this is a basic minimization problem where we have some objective function, in this case the sum of the squared residuals, and we have two parameters, alpha and beta. And so whenever we want to find kind of the minimum of a function, as we talked about in our kind of math pre-fresher, whenever we want to find the minimum or maximum of a function, the first thing we have to do is we have to take the first derivative with respect to the underlying parameter and set that first derivative equal to 0, right? And so first, in order to find alpha, our intercept, what we can do is we take this this function, the sum of squared residuals, and we take the first derivative with respect to alpha, right? So here we have the notation for the partial derivative with respect to alpha of this function. And note here that in this sum, the yn and the xn, those are all observed. This is our data for each individual observation from 1 through n. And alpha hat and beta hat are now our parameters that we want to estimate, okay? And so when we take the derivative, the simple chain rule here suggests we take the derivative with respect to alpha, and so this becomes -2 times the sum of this residual function, right? So this is basically just the chain rule, 2 times the outer function is squared, so this becomes 2 times the function, and we have to add this minus because, of course, the inner function, if we take the derivative with respect to alpha, that is just -1, so -2 times this remaining term. And so we have to set this equal to 0 in order to find a minimum for this function, okay? So the first thing we can do is, of course, we can basically get rid of this -2, so divide by -2 on both sides, and on top of that, what we'll do is we'll divide by n, and then we're left with this term. We can further, once we divide it by n, we can kind of multiply out this kind of go through this sum from n equals 1 through n, because if you look at individual elements, if you remember kind of the rules for sums, we can kind of separate each of those individual pieces with the sum operation. And if we look at each individual piece, 1 divided by n of the sum from n equals 1 through n of yn, that's just y bar. That's just our average y. 1 over n of the sum n equals 1 through n of minus alpha hat. Now alpha hat is constant across all n's, right? So this is just n times alpha hat divided by n, so this just drops, this just stays alpha hat, and then we have our minus beta beta hat xn, and here the same argument applies that we had with yn. If we sum over all xn's and then divide by n, this is just x bar, so so the average of x in our sample, okay? So basically we can simplify this to y bar minus alpha hat minus beta hat x bar, okay? And we can then easily rearrange and put y bar and beta hat x bar on the other side, and we're left with alpha hat is equal to y bar minus beta hat x bar, okay? And so this is already now alpha hat is only a function of y bar and x bar, which are just the averages of our dependent and independent variable, and our beta hat, right? And we'll basically leave this for now. We have basically a specification for alpha hat that depends only on data that we observed, y bar and x bar, and on our beta hat itself. And we'll proceed now by proceed now with specification for beta hat. And once we have beta hat, we can plug that into our formula here for alpha hat, and we get our estimator for the intercept, our estimate for the intercept. Okay. And one thing here to note that this formula is basically equivalent, or basically implies that the regression line always intersects with the point y bar. Y bar and x bar, because we can also rearrange this. We can also kind of rearrange this, put y bar on the other side and alpha on the right hand side, and then this equation becomes y bar equals alpha hat plus beta hat times x bar, which is equivalent of saying that the regression line always intersects the point x bar and y bar. That was one of the kind of observations that we talked about previously that is basically implied by this specification. Okay. All right, so now we have our specification for alpha. Next, we need to find our estimator for beta, so that we have a beta hat that we can actually plug into our formula for alpha hat. Okay. We start again with the sum of squared residuals, and we now take the first derivative with respect to beta, so with respect to the slope coefficient, and again we're setting this equal to 0. The underlying goal, of course, is still that the sum of squared residuals, in order to find the minimum of the sum of squared residuals, we have to find values for alpha and beta for which the first derivative is equal to 0, because that's how we find minima for any type of function, really. Okay, so again, we take the partial derivative with respect to beta of this specification of the residuals, which is yn minus y hat, and y hat, of course, is alpha hat minus beta hat xn, okay, squared. Again, we have to use the chain rule. It becomes a little bit more difficult because we have beta hat xn here. So this becomes minus 2 times, and then again the sum from n equals 1 through n. But then there's an additional xn, which comes from kind of the derivative of the inner part of that function using the chain rule. The derivative of minus beta hat xn with respect to beta is just minus xn. Okay, so that's why we have an additional xn here, and again we set this equal to 0, right? Now after setting this equal to 0, we can go through the same step. We can basically divide by minus 2 and divide by n to get this specification. And then multiply out this xn times yn minus alpha hat and so on to end up in this part. Okay, and now we're going to do the same logic again. We're kind of looking at each part of this the sum or the subtraction here, and kind of evaluate the sum from n equals 1 through capital N divided by n. Okay, so we basically separate these out. We have one xn yn as a sum divided by n, which we leave like this for now. Then we have this argument that we kind of saw previously when we talked about alpha, deriving alpha hat, which is 1 over n times n times the sum from n equals 1 through n of minus alpha hat xn, right? If we sum all these xn's together and divide by n, what we get is, of course, x bar, the average x, right? So we can basically write this as minus alpha hat x bar. Okay, this is basic summation rules that we talked about in the math refresher. So if you're kind of lost right now, feel free to, or please go back to the math refresher videos and some of that material and review that, and then come back to this video. And again, we do the same thing here, where we can't really do anything right away with xn square, or the sum from n equals 1 through capital N divided by n of xn squared. But what we can do is this beta hat, of course, doesn't have a subscript n, so this is kind of a multiplying some variable by a constant in a sum. We can pull out the product term, so pull that in front of the sum, so we have beta hat times 1 divided by n equals 1 through n, sum of xn squared. Okay. And now we basically take these two terms, alpha hat x bar and the second term, and put this on the other side to have this equation. Okay. Now, the next thing that we're going to do is we will plug in the result for alpha hat in the second equation. So see this alpha hat here, alpha hat times x bar. What we're going to do is now the result for alpha hat that we had previously, alpha hat equals to y bar minus beta hat x bar. We're just going to plug this in here, so we're getting rid of the alpha, and this becomes only a function of beta, as well as the stuff that we observe, which is x and y. So after we plug this in, this stays the same. We have, this is now our old alpha hat that became y bar minus beta hat x bar times x bar, and this stayed the same as well. Okay. Now we can rearrange this a little bit by first multiplying out this product. So this becomes x bar y bar minus beta hat x bar square. So this is x bar times x bar, and the rest stays the same for now. And then the next thing we can do is we can move this x bar y bar on the other side. So we subtract x bar y bar on both sides of this equation, so this ends up being here. Okay. And then the next thing is we can kind of multiply out this beta hat. This is part of both of these parts of this sum, so we can write this as beta hat times, in parentheses, x bar square plus this sum. Okay. And now we're going to do something in addition. Well, I mean, all we're doing is basically just the x bar square here, or minus x bar square here, is then just put at the end rather than in front. Okay, so this is just rearranging this a little bit, putting this at the end. Okay. The important part is pulling out this beta hat and having the rest of the sum or the subtraction here between this sum and x bar square in the parentheses. Okay. Now what we can do, after we have this specification, we can now take this part of, or this product, or this part of the product, and divide on both sides by this this part to get this on the other side, right? And so the underlying goal here is, of course, to get beta hat on one side of this equation, and all the other stuff, which is just things that we observe because that's our actual data, on the right hand, on the other side. Okay, so I'm going to divide on both sides by this term, and then have beta hat on one side, and I'm going to put this on the left side. Okay, so what we're left with is beta hat is equal to, we have 1 over n divided by 1 over n times the sum of n equals 1 through capital N of xn times yn. This is just this part here, minus x bar y bar, this is here, divided by this expression, which is just the expression up here that we divided, or that we divided by on both sides. Okay, so now we have beta hat, our parameter that we're interested in, is now just a function of things that we observe. Xn and yn are just the individual observations for each or the individual values for each observation that we observe. that is in our sample. X bar and Y bar are the averages. X bar square is the average squared, and the sum of the squared x's. Okay. And now we already have basically beta hat as a function of observable observed data. So we can basically plug in our data and get our beta hat. But we can still rearrange these a little bit to make this look a little bit nicer, and also make it look more consistent with kind of the specification in the book. Okay. First, we can kind of rewrite these as averages again, and this is just to make things a little bit easier. Rather than writing 1 over n times the sum from n equals 1 through capital N, we just write the expectation. Okay, so we just replace this kind of part with the expectation of xy. Okay. So rather than having this sum divided by n, we just write the expectation of x times y. And similar here, x bar and y bar are just the expectation of x and the expectation of y. So we'll replace this but with expectation of x times expectation of y. Same down here, expectation of x square and the expectation of x squared. Okay, so note here the difference. One is the expectation, the average of the x squares, and the other one is the square of the average, or the square of the expectation of x. Okay. So now after we have this, we can rearrange this a little bit more, and we'll do this step by step. First, we're going to focus. So this is just the same equation that we have down here. I just wrote this up here again so that we have it. Okay. The first thing we're going to do is we will focus on the denominator, e, or the expectation of x squared minus the square of the expectation of x. Okay, and this is just down here. This is the denominator. Okay, and we're going to use a little trick. We're going to expand this equation by adding something and directly subtracting it. So we're not actually changing anything, but that will allow us to kind of rearrange things in a format that will make sense later on, essentially. Okay, so we have this ex squared, so the expectation of x squared minus the square of the expectation, and what we're going to do is we will from this part we will subtract the square of the expectation again, and then we add the square of the expectation. Okay, so obviously these two parts, the lower two parts here, minus ex squared plus ex squared, they just cancel out. That's just 0, right? So we're not changing any math here. We're just subtracting something and then we're adding something, right? But if we do that, we can rearrange things a little bit. Okay, so since now we have this minus ex squared twice, we can rewrite this as minus 2 times ex squared. Okay, so now after we subtracted and added this term, now we're combining these two terms here and writing them as minus 2 expectation of x squared. Okay. After we did this, we can also rewrite the expectation of or the square of the expectation of x as the expectation of x times the expectation of x, right? So rather than having the square here, we're just writing this as expectation of x times expectation of x. Again, this is still mathematically equivalent. Okay, we're just rearranging things a little, or we're just kind of re-specifying things a little bit. Okay. And now, after we did this, we can also kind of use some of our rules regarding expectations, and we can basically kind of include things in the expectation or move things out of the expectation, right? Remember that we talked about some of the rules where you can kind of pull things out of the expectation or include or put it inside the expectation. And essentially what we're doing here is we're putting everything in one large expectation, which allows us to write this as the expectation of x squared minus 2 times x times the expectation of x plus the expectation of x squared, and this is where the second expectation ends. Okay, So now this might look like weird, a weird step, but again, if you think about kind of our expectation rules, and if we kind of were to take the expectation, and remember always the expectation of a sum is the sum of the expectations, right? So if we just focus on this last part here, and we took the expectation of this, we would end up with the expectation of x squared, which is just this part, then minus the expectation of 2x times the expectation of x. And of course, this would then again, taking that expectation would basically reduce to the expectation of x times the expectation of x, so up here. And this would just stay the same. The expectation of the expectation of something is just that expectation. Okay. So even though this looks a little bit weird, it's important to realize that this is still equivalent to the specification that we have up here, right? We're just moving things into the expectation, okay? But the important thing is that this is a basic kind of a quadratic formula that we can now simplify a little bit, right? So remember, whenever you have something like a plus b in parentheses squared, that's a squared plus 2ab plus b squared, or I should say a minus b squared is a squared minus 2ab plus b squared, right? So essentially what we did is we created a we ultimately created a pattern that looks just like such a quadratic formula, which we can now basically, kind of revert that step and write this x minus the expectation of x squared. Okay, so again, if we multiply out this square, we get back to exactly this this equation. Okay, and now lastly, we can now kind of revert back and kind of recall what the expectation ultimately is. The expectation is just the sum of all elements divided by the number of elements, so 1 over n times the sum from n equals 1 through n of the individual elements xn minus, and the expectation of x is of course x bar. Okay, so that means the denominator that we have down here, right, is equivalent, even though it doesn't directly look that way, it's essentially equivalent to 1 over n times the sum from n equals 1 through n times xn minus x bar square. Okay, so now we have basically rewritten the denominator of our beta estimate, or of our beta estimator. Now we do the same thing. We follow the same strategy for the numerator. So now we look at this part up here, expectation of xy minus expectation of x times expectation of y. Okay, so we're basically using the same strategy. We're expanding this equation by subtracting something and adding something, ex times ey, so the expectation of x times the expectation of y, and we add it up again, right? So again, we're not changing anything. The equation is still valid. Okay, then we're doing the same kind of rearranging and summing up these or including these or moving these inside the expectation, where we have now the expectation of xy, this is the first element here, minus x times the expectation of y, this is just this part moved down here, but now since this is inside the expectation, we can basically remove or have this x basically individually. Then we do the kind of remove the expectation from y for the second element here, so this moves down here, and the y loses basically the expectation because it's all taken care of by this larger expectation. And then we have the last part, ex times ey. Okay. And again, this is basically a product that we can rewrite as x minus or x minus ex times y minus ey, right? And so this is again kind of just, you can validate this going backwards by multiplying out this product. We get x times y minus, and then x times ey, so that's this times this is this, and then minus ex times y, this is this, and then minus ex times plus ex times ey, that's this part. Okay, so again we're just kind of rearranging the expectations here. Okay, and of course now we can replace these expectations again with our 1 over n times n equals 1 through capital N of xn minus x bar times yn minus y bar. Okay, so that basically takes care of the numerator. And now if we put everything together, we replace what we have up here with what we kind of rearrange down here, and that means beta hat is equal to 1 over n equals 1 through n of xn minus x bar times yn minus y bar divided by 1 over n equals 1 through n xn minus x bar squared. Okay. I forgot. This is just exactly the same. Oh no, sorry. The last step is since we have 1 over n in both the numerator and the denominator, that just cancels out, and so we're just left with these two sums. Okay, and the thing to note is that this exact expression is the OLS estimator the way it was shown in the textbook, right? So now we went step by step from our beginning, which is starting with the residual sum of squares, and we know we want to find the minimum of those residual sum of squares as a function of alpha, or to get a value for alpha and beta that kind of minimizes that residual sum of squares function, where every other part, the x's and the y's, are observed, and now we have the OLS estimator derived based on that starting point in exactly the format that you actually saw in our textbook. All right. Now, in the next video, I'm just going to take a brief break, and in the next video, I'm going to show you how to use these formulas for the OLS estimator to directly program this in R.